Hi, I'm so honored to host the 7th Smart Energy Conference at Afeka. Unfortunately, due to the corona, this time it will be virtually. Hopefully that our next conference would be in live and I will see all of you here at Afeka. I would like to invite Dr. Anat Rotnovsky, our Vice President of Academic Affairs from Afeka, to welcome our conference attendants.
It's my pleasure to welcome you all to the 7th International Conference for Smart Engineering in Afeka, and to welcome all the participants from Europe and Israel. I think this meeting is a great platform to exchange ideas and needs and new development in this field. As Moshe said, unfortunately, the meeting is now held virtually. However, although all of us had a very tough year, some of us are still waiting for the vaccine, as I heard from Moshe. We can start seeing the light at the end of the tunnel, and as Moshe said, I hope to see all of you next year in Afeka. I want to take this opportunity also to congratulate Professor Ariel Avneri for the opening of the MSc in Energy and Power System Engineering with the thesis. The opening of the new program shows the recognition of the CHE, of the importance of this subject, and of Afeka as a leading academic institution in this field. I wish you all a very interesting meeting, and want to thank Dr. Moshe Tshuva for organizing this meeting. Thank you, Moshe, and enjoy.
Thank you, Anat. It was nice to hear. I would like to invite Professor Ariel Avneri, the head of the new MSc program in Energy and Power Engineering System at Afeka. Ariel?
Thank you, Moshe. And on behalf of the new MSc program in Energy and Power Systems Engineering at the Afeka College of Engineering, it is a great pleasure for me to welcome the attendees to the 7th Smart Energy Conference. The purpose of this conference is to bring together energy systems and electric power experts from academia, from industry, government, and other organizations to discuss the latest developments and challenges in this field. And Dr. Moshe Tshuva has gone to great lengths to plan an event that meets a high academic standard. And we will have an opportunity to hear international speakers who will share with us leading edge studies that cover a wide spectrum of energy and power systems engineering, from heat storage and air-to-water heat pumps to innovative transportation systems and smart buildings. And we would like to thank you all for choosing to attend this conference. And I really hope it will be interesting, enjoyable, and valuable for you. Thank you.
Thank you, Professor Avneri. Yes, indeed, I think that every subject in the program could be a different conference, and maybe it's a good idea for the next conferences. Maybe we will do a conference dedicated to each of the subjects: smart building, the smart transportation, and so on. Yes, it's a good idea. I would like also to invite Mr. Dave Rosenberg, the energy supervisor from Strauss Group, to welcome our guests. Dave?
Yes, hi Moshe. So as Moshe mentioned, I'm Director of Energy Efficiency at Strauss Israel. And I would like to thank both Michael Stolberg and Dr. Moshe Tshuva for making this today conference happen. Strauss, as an international company whose home is base is in Israel, is considered the largest food and beverage company in Israel. Strauss is proud at its pursuit for excellence and being a leading company in adopting innovative technologies as well as in investing in startups. For this reason, we believe in the importance of taking a leading part at the joint offer of the Israeli industry and community to improve energy efficiency. The energy form of energy and saving, which I was brought to lead with the assistance of Michael and Moshe, is a technical home for people who care about how to improve energy efficiency in their organization, doing good both for the organization as well as the contributing to the world. This conference will help us to provide more knowledge about braking technologies. It is important that the academic community will be the engineers on the industrial world ambassador and get updated with the new developments and technologies. It will be their goal and task to learn, test, absorb, and transfer this knowledge to the entire engineering community and energy community. So once again, I want to thank you for this interesting conference. Good luck.
Thank you, Dave. Dave mentioned well, we are trying to do some combination of combining the industry with the academia and trying to improve the energy consumption, the energy efficiency in different industries. Meaning, as you can see, even if you will try just a little bit to improve the energy consumption in industries, you can earn or you can benefit quite a lot. In fact, every kilowatt that we will save will improve the system, will, of course, economically will improve the total benefit of the industries, but it will allow us to not to build new power station. So, but then in industry, not all the people are really into the subject of energy efficiency and how to improve the energy consumption in the industry. That's the reason we had this forum, the Forum of Energy Efficiency and Saving, and we invite all of you to join this forum. So, well, we can start the conference. As I said, it would be 15 minutes per talk and 5 minutes per questions. I will be in charge on the time, so I will tell you when it's time to finish. And our first speaker is Dr. Athanasios Kalogaros, my colleague and friend from the Research Center Athena in Greece. I've been there, it's quite a nice place. He will speak about residential smart building energy load profiling. Athanasios, please.
Thank you, Moshe. Thank you for the invitation and for being here. I wish it was possible to be in Tel Aviv live and see you all in the proximity, but anywhere the pandemic does not permit us. Maybe next year, or even better, during the summer, some of you could come to some Greek island, and this could be, we would be very happy to welcome you. So I'm going to share my screen. My talk, as you said, is about residential smart building energy load profiling. It's a work that is done in a European funded project called eSmart City, which is related to smart cities and is funded under the Interreg Med program. Before getting into my presentation, just one slide about my organization, the Industrial Systems Institute of the Athena Research Centers. It is an institute that focuses mainly on industrial systems, so the main research areas are intelligent systems and robotics, real-time and networked embedded systems, manufacturing systems, processes and enterprise interoperability, enterprise information systems, security and protection of systems, networks and infrastructures, and advanced materials and structures. We have a strong focus on the so-called fourth industrial revolution from the point of view of cyber physical systems, systems that combine the cyber dimension and the physical world. And this means to deploy sensor infrastructure, the so-called industrial Internet of Things, get data out of it, exploit cloud and edge computing models, and on top of it, apply machine learning and artificial intelligence to have advanced services. So the motivation behind our problem is that urbanization is a trend in our world. So 60% of world population will be living in cities by 2030, and the urban population is increasing by 1.5 million per week. And cities account for 60 to 80% of global energy needs. So actions taken in cities can have a significant impact in energy saving and energy efficiency. When it comes to buildings, buildings use about 40% of total energy and 70% of electrical energy, and they account for 1/3 of greenhouse gas emissions. With reference to energy consumption in domestic buildings, in homes, there is an average yearly increase of 1.4% in the period 2012 to 2040, with the increase in non-OECD countries being 2.1% and 0.6% in OECD countries. And the 5 primary energy uses in domestic buildings is space heating, space cooling, water heating, lighting, and refrigeration. When it comes to the commercial sector, the average increase is 2.1% in the same period, and in non-OECD countries is 3% annually, and in OECD countries is 1.6%. With 5 primary energy uses being here lighting, space heating, space cooling, ventilation, and water heating. So the project stood up to this challenge and performed some pilot testing in 6 different countries related to 2 cases, energy efficient buildings and public street lighting. And to this end, we had 4 public lighting networks in Sarajevo, Bosnia-Herzegovina, Lyon, France, Pescara in Italy, and 2 municipalities near Granada, Huetor Tallar, and Agron in Spain. And then we had a second case involving public buildings from the point of view of energy efficiency. And so we had a total of 53 public buildings in Greece, Italy, and Portugal. And the project produced a strategy document, a green paper on innovation policy change to drive towards smarter cities, which is available and can be downloaded from the project website with some policy recommendation to this end. The pilot case, one of the pilot cases associated with energy efficient buildings was employed at our building at the Patra Science Park, which had as a goal to experiment with energy efficiency and living lab scenarios, deploying the necessary infrastructure for monitoring, controlling, optimizing, and testing energy efficiency. And to this end, The infrastructure installed comprised smart devices, Internet of Things, and smart embedded devices with different types of connectivity, wireless mainly, utilizing edge and cloud computing, and finally employing big data analytics on top of it. The specific goals was to take advantage of high performance IoT technology, to integrate diverse devices with with a lot of heterogeneity, so to prove interoperability between solutions, to exploit open source solutions wherever possible and be based on standardized protocol, to adapt a suitable distributed embedded infrastructure, to utilize edge computing and cloud computing so as to exploit the intelligence at the edge of the network, to utilize industrial and Internet of Things data acquisition platform, to finalize and deliver smart monitoring and control solutions integrating big data analytics for energy consumptions and providing optimization of user comfort. And the solution provided is scalable and replicable and can be transferred to other sites. So the proposed system comprised different types of parameters. So there was power consumption, light, humidity, temperature, and human presence that were measured in the building. Here is an image from the final system with the location of the different devices installed. And here is a panorama of the different technologies. So you can see from the hardware point of view that different solutions were integrated, both proprietary and open source. Also different communication technologies were utilized. And finally, different software platforms were integrated to provide the overall solution. The architecture that we used involved the measuring equipment and the IoT equipment at the edge tier with different communication technologies, Zigbee, Wi-Fi, and interfacing to the platform tier via the MQTT protocol. A NoSQL database, Cassandra, was used, and the information finally passed from a commercial platform Things board to the enterprise layer where the intelligence of the system resides. Here just a few photos of the different sensors that were utilized. So depth cameras, motions, smart meters, and the monitoring and control room of the overall infrastructure build. And the HMI with the monitoring, providing different types of views so as to be possible to see the energy consumption and the different other measurements at the building level and on the different offices and laboratories. And finally, some control is also possible to be done via the system, and optimization with rule-based mechanism for scheduling and optimizing the power consumption. So the overall idea is that there is a data set that comprises the different measurements from the building. And then the question is what you do with this data, how you analyze them, and how you exploit the data towards achieving more advanced features. So here we tried to see how we can deal with imbalances in energy demand and steep demand surges disassociating the demand time span with renewable energy production, and with a goal to detect load profiles whose peak demand could be not according to the power grid. As Moshe said, this might be a very important factor because otherwise you should build more power plants, etc. So some ideas about energy profiling. This is a powerful tool for estimating the overall energy consumption. And you can use static factors like the building orientation, the occupancy of the building, the environmental conditions, etc., that can contribute to estimating the energy consumption of a building. And there is also the dynamic dimension that can be based on energy metering and can utilize the data, the exact data from the building. So data mining can be exploited, and machine learning algorithms can be employed in order to dig and find patterns in the data that can reveal you some interesting results on your building. So the outcomes may be exploited for different applications, for demand forecasting, for optimization of energy generation, for energy pricing and monitoring and diagnostics. The challenge behind energy profiling is that you have to take into account vast amounts of data that are both real-time and historic, and which are generated by smart metering devices. So if you install a number of smart metering devices and a number of sensors in the building, and the larger the building, this quantity of data becomes enormous, and so you have to quick process them in real time and be possible to extract the knowledge out of it. And so there is a need for new methodologies such as data dimension reduction and time series processing. And there should be a trade-off between the losses that you have due to the data that you drop away. So there is an error there, and the amount of data that is condensed. And to this end, a tool that can be used is variational auto-encounters, which is a family of unsupervised learning, and which provides robustness and efficiency to handle patterns in vast amounts of data. So our proposal was to employ such mechanism and enhanced variational auto-encounter, applying recurrent neural networks in the encoding and decoding modules at the start and the end. You can see that there are two units called LSTM encoder and encoder, and which stands for long short-term memory neural networks, which are used to encode and decode data. This autoencoder is trained to output the given input data series with the beginning and the end module, the encoding and decoding module, replaced by recurrent neural networks so as to captivate time dependencies. In order to evaluate experimentally this approach, and due to the fact that the data set that we had from our building was too short, so it was 1 year, and we needed the larger data sets to proceed. We took into account a residential sector data set from London, which is an open data set that can be derived from the address that is depicted on the slide, and which contains identifiers for the different residencies the specific date and time of the measurements, and the power consumption on the residential building. And based on this, we made the comparison between different types of autoencoders. And here you can see the loss from this. So the variational recurrent autoencoder loss is the lowest one in comparison to the variational autoencoder and the autoencoder loss that are the other two graphs. And based on this, we limited the residential buildings into two clusters. One cluster that is compliant with green energy and modeled according to the green energy supply. So imagine that you have some photovoltaics on the building, and so they produce some electricity. So we clustered the buildings into two categories. One, that the power consumption is according to the generation of energy, and one that is complementary. And we encoded the cluster representatives according to the variational autoencoder. And here you can see the two cluster characteristics. So the second is the cluster that is somehow compliant with the energy consumption of the power generation by the renewable energy, and the first is the complementary of this. And we did different experiments with other types of tools, so K-means and spectral clustering, in order to see which worked better. So the first figure shows on the top the K-means and the spectral clustering, and you can see that they failed to capture the peak demand for the two clusters, while on the right you may see the variational autoencoder, and you can see that there is a compliance and a disambiguation between the time series for the two types of clusters. So on the right, sample 2.2 is about the renewable energy compliant cluster with the peak of energy consumption according to the graph in the previous slide, and the second, the sample 1.2 on the left is the non-renewable energy compliant cluster. So the result is that actually the variational autoencoder method makes it possible to disambiguate and provide useful information related to the clusters of the buildings, and this allows you to drive some good results with reference to this. So this is a first effort. We are continuing our work towards this end, and trying to include a larger parameter set further to the renewable energy produced at the building site. And this can be an initial stage of some work on a wider energy profiling attempt. So thank you very much for your attention, and I can be at your disposal for any discussion.
Thank you, Athanasios. Very, very interesting. I want to can you make it clear? You add the information from your building at the Patras and also from some other places in Europe, 6 places in Europe, and you also took the information from the London municipality, right? So you took the whole information?
No, the first part of the presentation was about the deployed infrastructure, but as the project ended on August 2020, the actual data set that we had was about 1 year long. So we opted, in order to test the algorithm, to use a data set from a set of buildings in London. So we did not use the data set from our building in this training. I think the plan is at the end of 2022, when we will have a 3-year collection, a data set that spans into 3 years, that it will be possible to be used in order to verify the result. So we took an existing data set that is, let's say, 10-year long, and we trained the algorithm, and so we got into some results based on this data set. So the work, the second part of the work presented did not utilize the data set from the eSmart City project.
Yes, because I also, I mean, I gave it as in a seminar to our student in the second degree. I gave also the data set from the London municipality. It's very good data set, and they can distinguish between different types of buildings, different types of customers, and yeah, it's a very good information data source over there. Yeah. Okay, thank you. If anyone has some more question, you can add it on the chat, and I will ask Athanasios. Anyway, we have to keep our schedule. So thank you very much, and I really hope to see you back in Israel or at Patras, which will come first. Thank you, Athanasios.
Always welcome.
Yeah. I would like to invite our second speaker, Dr. Gur Mittelman. He's a staff at the School of Mechanical Engineering at Afeka. Gur will speak about energy supply to personal rapid transmit PRT systems. Gur, unmute yourself. You're muted. Gur, can you unmute?
Sure. Can you hear me? Fine. Is that okay? Can you hear me?
Please share the presentation.
Sure. Can you hear me?
Yes, it's good.
Very cool. Okay. Okay, so thank you, Moshe, for the opportunity. And this topic is about personal rapid transit systems. And this study was conducted here at the Afeka, together with my partners, Professor Ariel Avineri, Professor Yuval Cohen, and Engineer Yaron Karib, who actually received his master's degree here at Afeka. So I think the problem is all very familiar to all of us. Big traffic jams all over the world. Actually, 2 days ago, some of my students were late for the class because of a tremendous traffic jam taking place at in Tel Aviv. And the question is, can we do something about it? So one approach is the PRT. PRT is a personal car, probably electric vehicle that comes by demand, under demand. It carries maybe 1 or 2 passengers. And it's not a new idea, probably known since the 1970s. And there are already 3 or 4 commercial demonstrations all over the world, successful demonstrations. And the idea is that you can get from anywhere to anywhere within your town, from a station to a station. If everything is connected or interconnected, you can get anywhere, and you don't have to stay in the jam, and you don't have to look for a parking lot, etc., etc. That's very, this could be very, very pleasant, actually. So what we are interested here in our research is we were interested in the energy supply thing. the energy management thing here. There are a lot of issues here, but we were focused on the energy supply because this is an interesting problem and valuable as it is. And there are a few options here. There's the battery, like any electric vehicle. And there are the other options of electric rails, like overhead catenary, which it's very, very common. Also the third rail, whereby people put another rail next to the driving rails to provide the electricity to the vehicle, to the train, probably. And there is the magnetic levitation, but this magnetic levitation is rather new technology. It's not yet well proven, no big commercial demonstrations, and also not a lot of data to work with. So we decided to focus on two options, battery or third rail. Overhead is a good one, but in very dense cities, when the streets are narrow and there is not too much space for this infrastructure, overhead will be problematic. So we are left with two options, which we consider attractive or generic, like third rail conductor and battery storage. So what is the objective? Is about developing a modeling and also implement it to the entire energy management system from the grid all the way through the battery and the powertrain and other elements to the wheels, and also taking into account balance of plant components such as the stations and other things that we will see later. There was a work, very big work or study that was made, was published a few years ago about the attractive energy requirement without considering the entire system. So we decided to extend the model to include the whole system. It's actually what we do is actually to go from the wheels, from the tractive or propulsion requirement of the car through all the components to the grid. To get the whole picture about, to see the whole picture about how much energy indeed is consumed in this system, which is rather complex. So we picked a model. Our research is not about developing a new technology, okay? It's about modeling. So we picked up a vehicle model, which is a small car, electric car that is suitable for PRT system rails, with small dimensions, can carry up to 2 passengers, and with some data considering the resistive forces of this car. This is how we. This is our vehicle. But a vehicle is not enough. We have to consider the whole guideway system. So we choose for the case study the city of Herzliya with 11 stations and overall rail length of something like 12 kilometers. And some other parameters which we have to consider is how many cars do we keep. Some of them are moving and some of them are idle. Some of the cars are occupied with passengers, others are empty. This was also considered in the study. This is actually a result, what we see here is a result of a previous study made by, again, a group of researchers from Afeka. That they were not interested in the energy problem, only in the infrastructure and the design. So this is the resulting data of their work. Now, we consider that the train or the pod car, the taxi, the car, whatever we call it, it's accelerating from the ground level, picking a passenger from station 1, say, and then cruising for the most of the distance, which is good from energetic point of view, because when cruising, the power requirement is minimized, and then braking to the other station. This is a typical network between 2 stations. And about the kinetics, this is rather standard mechanical physics. There are 5 forces acting on the vehicle. 4 of them are resistive: drag, rolling, gradient, and acceleration, if any. Of course, during the cruise there is no acceleration, but in general we have 5 forces. And the very important thing is what happens while braking. While braking, the car has energy, and the question is, can we generate electricity or energy while braking? Well, the answer is depending on our design. If we have a battery, for instance, then we can, because we can charge a battery. If we don't have a storage device, we probably cannot do regeneration without significant technical complications. So we also consider this effect in the study. So the kinematics is going pretty much as follows. You have the acceleration is changing. This is coming because this is a result of the comfort requirements from any vehicle. The vehicle can never drive under a constant acceleration condition. So the acceleration is increasing up to some limit, which is defined by literature. According to the comfort, it's 2.5 meter per square second. And and then cruising, and then while braking, acceleration is of course negative. And the tractive force and powers is, not surprisingly, is at peak at the end of phase 1, because the drag force is highest. The velocity is already cruise, and the drag force is highest at this point. So this is the most of the tractive power that you're going to get. And the tractive power, as we see, is not fixed. It's not fixed by time. It's changing with time all the time, the tractive power. This is very important because if we consider a constant voltage systems and the power is changing, that means that the electrical current is going to change with time. And this is very, very critical for the energy loss and the design of the grid and battery system. So for the battery bank, we consider a standard lithium-ion battery as like state-of-the-art, commercial available batteries. Many companies have developed such batteries, like Tesla. And we must consider the operating temperature. The battery must work in order to keep a reasonable lifetime and not getting dead very quickly. One need to maintain the temperature probably below 30, maybe even close to 20 degrees. But that means that you must cool the battery. Must cool the battery. Many people ignore that. This can take a lot of energy just to cool the battery, because otherwise your battery is going to be dead very, very quickly. For instance, Chevrolet electric car, which is one of the best electric cars that you have, they use liquid cooling. They put cooled liquid within the plates. The plates are located in between the battery cells, and this is how they maintain the temperature. But this is of course costs electric energy, because in order to cool, you need some air conditioning or some compressor or something like that requires a lot of electricity, and you must account for that kind of consumption in your analysis. And our analysis resulted in a battery of 44 kilograms for a loaded car. This is the result, which is not negligible, because the whole vehicle is small, is maybe 500 kilograms, so this is not negligible. And we considered, of course, that the battery can be recharged while braking. Third rail is the other option that we analyzed. And here there is no battery, but there are other issues, like we have to supply, you have to convert AC electricity from the grid to the rail. Therefore, we need to have a power system. and there will be energy losses during the, throughout this power system that we have to account. And those energy losses are again depending on the power or on the current, the electrical current that we provide to the rail or we get from the rail while braking. So this was also taking we also took this one under consideration, and we also accounted for the balance of plant issues. When we have a complete PRT system, it's not a complete system. It's not only about vehicles. It's also you also have to keep stations, passenger stations. They consume electricity and sometimes a lot of electricities, and there is vehicle auxiliaries like air conditioning, lighting, etc. And also there's the powertrain of the car. It's not just the wheel or the tractive power. There is a powertrain in the car, and here we did something that probably never was carried out before, which is to model the grid and the battery, which means we don't use a simple single value for the efficiency for the grid or the battery, but we model it according to the current or the power. As I mentioned before, it is much more accurate and much more realistic because this is what's happening actually in a real system. Okay, and just to complete the data, because we were opting for techno-economic model, we have to consider some economic values. So we have to pay for the electricity coming from the grid, unfortunately, but and we have to install the battery and the charging stations together with the grid connection. Battery, by the way, is not just the battery, it's the entire battery management system, as they call it, BMS, and the cooling system and the power power engineering that is involved with the battery system. Everything has to be accounted for. And in the third rail solution or alternative, we don't have a battery, but we have to electrify the rails, which can be very expensive. Unfortunately, we don't have data. We don't have data for third rail, which is suitable for small PRT vehicles. So we use a value which is available for large trains. We think that it might be not so accurate, okay? But we don't have anything else, so we use this value, which can be too much oversized. Like for the PRT, probably the electrification, because the PRT is a small vehicle, is based on small vehicles, it could be much cheaper actually, but we don't have a reference value, so we don't consider them. Okay, and grid connection also for the third rail, of course. So the results, the bottom line is we try to compare the energy consumption of the several alternatives. So we have two alternatives in our work, battery PRT or third rail PRT. And we have a reference PRT data because commercial PRT, there are few commercial demonstrations already for PRT, so we can compare to. But we can also compare to other transport alternatives which are not PRT at all, like tram or metro or public buses or private electric cars and so forth. So the results, and we measure the results by the kilowatt hours per passengers per kilometer. Okay, so that's normalized energy consumption. How much it costs to take one passenger, how much energy it requires to take one passenger 1 kilometer. This is very common measure. And we see that the battery is the best. Third rail is not bad at all. And the PRT as a whole is much better than any other transport option that we know about. For instance, private electric car is consumes much more energy than PRT, which is very, very remarkable. result, which means that PRT in terms of energy is very, very efficient. And the cost, we got the cost of the battery option is much lower compared to third rail because, again, I think it's because the third rail electrification data that we used is based on the large trains and not PRT. So that might be the reason, and we can extend the work further if we refine the models to better model the powertrain and the battery thermal management, which is a big thing in batteries, and also include the issues that were not taken into consideration here, infrastructure costs and environmental impacts. So the bottom line is that the energy consumption is relatively low, the cost is very attractive, but maybe the most important thing maybe about PRT is that if we had PRT in Tel Aviv, actually my students will no longer have the excuse why to come late to the class. So that's maybe the most important thing about PRT. So thank you, and I'm open to any question.
Thank you, Gur. Gur, we have one question from Nadav. He's asking about the concept. Is it a real project or only?
It's right now it's only a study.
A study.
But it's only a study, but but maybe Professor Erel Avineri can extend on this. But it's a study. But in order to push the decision makers towards installing real plants, we need to convince them first that it is cost effective and energy efficient, etc., and practical and so forth. So this is like we must do a study before we can convince anyone to make a decision. But I believe Professor Avineri is more educated about this issue of implementing PRT.
Okay, and Erel, you want to say something? Yeah, Erel.
Just to say it's not completely theoretical. There are few systems that are operated on a mini scales around the world. One system is operated in Heathrow in London, another one in Masdar City in India. So there are few examples of how this can be actually be implemented. Our model was using the most updated data. So it's kind of the next generation of PRT rather than the systems that are already been activated. Also, I see that Nadav asked whether it has some advances over the concept of light rail. So these are two completely different concepts, as this system is not supposed to transfer a large amount of people at the same time. It's more a concept that is competing the personal car rather than the light train or metro, as it's supposed to give high level of service and not sharing your ride with a large number of individuals like in the bus or in the light rail. So it cannot be compared at all. Not by its function and not by its energy consumption.
What about I think that I heard about Elon Musk talking about something like this, but underground with electrical vehicle, of course, Tesla electrical vehicle.
The Hyperloop concept is then again another completely different concept. It's about transferring people over very large distances. It's not relevant to the urban movement. It's more like interurban of many hundreds of kilometers. It won't be efficient, probably won't be efficient for the distances that are common for urban travel.
Yeah, I can see Dvir is asking about the range. There is a range in the kilowatt hour per passes per numbers. What is the impact in, is it so much?
Yeah, per passenger, it's the difference is due to the fact that there are different designs. Each system, each commercial system has a different design, different vehicle size, different kind of batteries, different kind of grid power system. I mean, it's the designs and the layouts are different. So you can get a range of energy consumption in such kind of analysis. We did too. We just did not present here in this presentation the sensitivity analysis that we carried out. We did not present it, but we did it ourselves. So there is in any energy management analysis, you will have some kind of uncertainty because your input data is not certain.
So I think we are a little bit behind schedule. So if you can answer through the chat, there were some questions. I think we didn't speak about the environmental impact, putting such a big thing, in the city. Outside, there's a lot of impact, a visual impact I'm talking about. Yeah, we didn't speak about it. But let's continue to our third speaker, Professor Karl Vernet, Vice Dean for International Affairs from Technical University of Liberec. Karl, it's nice to see you. It's nice to see you via the internet. I hope that we will meet, maybe in Tel Aviv. I didn't see you for a long time, so maybe we'll be in Tel Aviv. So Karl will speak about one of the main, the heat storage. He will speak about heat storage by the separation of silica gel.
So, thank you very much. I hope that you can see now my presentation.
Yes, we can see it and we can hear you. It's quite okay.
Okay, thank you very much once again. So, I'm coming from the Czech Republic, and I decided today to speak about our, I would like to say, results relating to the absorption of the energy or the storage of the energy. And we decided to use the sorption process because we have already several experiences in the field of the research. And I will be talking now about previous results and the new results. First of all, my area of the research, it's the area of the energy. And we are looking at the different kind of the problem. The goal is the same. That means to save the energy. And we mostly are focusing on the energy transfer, energy efficiency. We look as well at the technology which are used in the smart buildings and mostly connected with the energy storage. And of course, the one part of our research is focused as well on the smart materials and the material research, because a lot of, I would like to say, properties and the processes we can are just connected to the material research. So it's as well the part of our interest. First of all, what is generally the method which we use? So I will be mostly talking about the experiment and the CFD. The experiment, because I'm coming from the field of the thermodynamics and the fluid mechanics. So at the one side, we design the equipments in which we can just confirm or study some processes in order to understand in details. And secondly, in order to maybe improve facility or operating conditions. For those part of the experiment, we use a lot of measurements like the PIV, hot fire anemometry, and so on in order to identify the velocity field, in order to identify the temperature field, and how I said, to understand the background about the flow features and thermodynamics processes. As another part of our research, it's concentrated on the theoretical research, which is represented by the CFD, computational fluid dynamics. And for the calculation, we use the 3 different type of the computational codes. That means everybody maybe knows the answers. which is mostly very preferred in the students' work and diploma work and so on. Then I myself, I prefer to use the OpenFOAM, which has a lot of advantages. One of the most advantages that we have a source code, so we can extend this code to programming the parts which we needed to study. And in the past, I was working a long time on to develop the own computational code, which has a name, the VM or finite element method for 3D. And it's fully parallelized, used for the incompressible flow simulation. The most advantage of the own code is, of course, that we can completely control our computational processes inside. So this is the technology which we use, or the techniques which we use to carry out our research. And I would like to mention it at the beginning. And now I go slowly to the topic of our research. So the one of the topics is just the absorption process, which we use for the thermal storage. And we are just at the beginning. So our task or the goals today is to construct the facility using which we'll be able to demonstrate the feasibility of these techniques. And we are studying the material properties in order to reveal under which operating conditions we are able to effectively store the energy. If I tell you at the beginning some main aspect or the main facts about this kind of the heat storage, of course, everybody, we are talking about the heat storage. We can imagine the sensible storage tanks or the latent storage tank, which are commonly used. And with this technology, we have a lot of knowledges. On the other hand, it's possible to use the sorption process, which is relatively new. And using the sorption process, we can practically store and after that release more energy per kilogram of the materials, which is used with the, for example, sensible heat storage. And we have as well no problem with the change of the volume, which is the critical point for the latent heat storage system. And what is as well advantage that you can store a long time this heat without the heat losses. That means it looks like so, it looks funny because at the one side we store the heat, on the other hand, we have no problem with the heat losses, which I think it's just fascinating to carry out such kind of the research and to use this technology in the future for the heat storage system. So the main task today is to develop the facility, which is possible and which is possible to carry out the experiment and to respond to questions, which material is the best for the heat storage using the sorption process. Secondly, under which conditions we can use the maximal effectiveness of the storage system, and in general to, I would like to say, identified the best sorption process efficiency for the future facility. Before I start to speak about the particular results, I would like to mention it here, the previous results. This is what you can see. It's now the work from our student, PhD student. He has already finished the PhD study, and he started to research the sorption process for the CO2 capture, and as well using the sorption process. That means we use here the temperature to accumulate or to store the CO2 and again the release. And the system, it's control only the value of the temperature. Above, you can see just the experiment, which is very simple experiment. And inside, you will find the active coil. And using the temperature, we can actually capture the store or the release, or capture the CO2 or release CO2. And this temperature swing adsorption techniques, it's as well used later for the heat storage. So below, you will see the graphs here. And the graphs locate just or indicate the change of the temperature regarding to the change of the concentration. Not only the experiment, it's just the way how to just study this problem, But as well, we carry out the numerics. Numerics, it's just not easy to do it. In this case, we use the open form. And we look inside how this sorption process is working. And it could help us to understand how I said the backgrounds of the sorption process. The basic question is the effectiveness of the sorption process for the CO2 storage, and just the numerics and experiment. We carry out the both to just extend the experimental results by the numerical or the theoretical results, how I said, to find the appropriate, or to design the appropriate system which can store a lot of CO2 for a relatively small amount of the materials. There are two slides which demonstrated the previous research. Actually, 5 years ago, we started this process, or the study of the sorption process used for the CO2 storage. Today, we are going in direction to heat storage, but the sorption process and all the knowledge which we have already founded here, we can use furthermore. And now you can see some overview about the possibility to store the energy. And it is the liquid absorption, solid absorption process. We can use as well some kind of the chemical reaction and the composite materials. If you look now on this problem, we are going in direction to use the silica gel. This is the solid absorption. And the silica gel is the first one, using together with water. And the second one, it's ceolite, which is mostly the second option to use this material for the heat storage. What is the difference for us? Especially, it's the fact that the silica gel can work for a lower temperature field. So it's better for the experiment because we don't have to just heat up the air to so high temperature level. And secondly, the silica gel, it's very easy to have and or to purchase, and some material properties are well known. So this is the reason we decided at the first step to use the silica gel, and we have found the relatively excellent experiences. This is the first concept of the equipment which was just constructed or the design and constructed later for the experiment. And here in the container, which is indicated by the letter C, you will find just the silica gel material, which is homogeneously distributed. And we can change the different type of the mode. That means we just can dry up the material inside, or which is used to just to store the energy, or we use the, to release the energy, we use the second step. That means we mixture the air with the humidity, with the moisture, in order to start the chemical reaction. During this, we can release the energy again. How it's working exactly, I can just describe here. That means there are two steps which are in the cycle. That means they are repeating each other. And the first one, which is called like the absorption or the discharging, that means we have just the energy which is already stored in the sorption tube. And we deliver the moist air, which start the reaction inside, and practically the material can capture this moist. And as a result, at the output, you will find the hot air. On the opposite, if this sorption tube is already empty, we start the second step, during which we can actually charge this sorption tube again. That means we deliver only the hot air. We are calling about, or we are talking about the drying process. As a result, you will find the air and the water together with the lower temperature. And during this process, we can actually store the energy. And now if you create a cycle and you will repeat these two processes, so we can just discharge and charge the energy, and all it's about the time and about the frequency. Of course, the problem is that any materials can degrade during this process. And this is as well our topics of the research, and I can show you some results. So first of all, this is the amount of the mass absorbed, or the water or the humid absorbed in the material. If we just compare the kilogram of the vapor divided by the total amount of the absorbent. And as you can see it on these graphs, it describes the amount of the absorbed moisture regarding to the time. And very important, it's the first 20, 30 minutes in which we can absorb a lot of vapor into the materials, and the less the change is not so drastically to see. And what you can see as well, we have performed this test for several cycles. It's relatively time consuming because the first type of the experiment, it's not fully optimized. So it's a little bit difficult to perform a lot of cycles, but definitely from these results, we can see the degradation or the effect of the degradation of the material on the ability to capture the vapor into the materials. It is just the one first step which we partially describe furthermore in this publication, which you can see below. This degradation of the capacity of the ability to materials, the materials to capture the energy can be described if we look at the specific power, which is again described as a watt per kilogram of the absorbent which is used. And you can see as well the mean specific power, which is just demonstrated on this graphics on the right side. In both cases, we could demonstrate that after some specific cycle, the material just lose the ability to work properly. Of course, there is a trick that you can do the regeneration of the materials and you start the materials once again from the excellent condition at the beginning, but this is sometimes the problem. How I said, the previous experiment has or had the one big disadvantage that it was not fully optimized. So it was not possible to carry out more than 5-6 cycles because it was time consuming. So we decided to construct the new facility, which will be fully optimized. And we can just run this, experiment a long time to observe what can happen with these materials after many cycles. And this second, the second experimental device, it's very similar to this, which you could see before. Instead of the hot air, we are now use the fan, which use the heating of the air at the appropriate temperature. In our case, we are talking about the silica gel. For drying process, for the charging process, we use the temperature field about 20 to 70 degrees. And for the discharging process, we are talking about the 30, 35 degrees. So the temperature, how I said at the beginning, in the case of the silica gel, it's not so high. So we can, without any danger, to work with this hot air. And we can construct this experiment device. And now it's still under construction. We have already the first results, but we are still working on to fully optimize the process. That means during the night, we can significantly change or we can be able to change the cycles in order to just find the appropriate materials properties. So this is the conclusion, some summarize of our testing, which you could see now, that not only the first test, but as well the progress in the design of the second experiment. And of course, not only the silica gel is interesting, the zeolite materials is another materials which is very popular today to use for this purpose of the energy storage. And we are just thinking about to use this material as well in the future, but it requires the higher temperature for the heat storage. So this is all from my side. Thank you very much for your attention.
Thank you, Carl. Very, very interesting. You were talking about 70 degrees. What were the temperatures?
Yes, the temperature was up to 70 degrees for the silica gel. It means if you charging the energy, that means if we are dry up this absorbent in the container, we use the temperature between 50 to 70. And of course, the temperature can just influence the process itself. That means it is as well the part of our research. So we know that the material is working between this temperature field between 50 and 70, which is as well recommended by the producer of the silica gel. And for the discharging process, for the discharging process, we use the lower temperature. It's about 30 degrees.
So if you have some kind of residual heat, you can store it in some kind of silica gel.
Exactly,
and then...
exactly. This is just the excellent, for this temperature field, it's excellent conditions. We had two ideas how we can actually practically use this technology. The first one, it's the combination with the solar power. It means instead of the water, we can use the air. We can actually heat up the air in the solar panel, and this heated air, which can reach just about 100 degrees of the Celsius. We are not talking about the concentrated solar power. It's excellent as an input temperature for such kind of the facility. And we can, for example, store a lot of the energy inside of the silica L and can be used, for example, later during the night to release the energy. This is just one practical application, which is already possible to see today.
Yeah, thank you. Very interesting. I can see Non is asking about, did you consider the effect of high-low pressures?
Oh, very good questions. So the temperature is the one thing, the temperature, the pressure, it's another problem of the sorption. Of course, we can use the temperature to control the cycle. We can use the pressure. Today, we are working only with the pressure practically under condition of the atmospheric pressure. So our study just a little bit ignore the effect of the pressure on the sorption process. But theoretically, this question is correct because the pressure can influence the sorption process itself, but it's not the objective of our study.
Okay, thank you. And I will mention that some of our students will come to your laboratory to work on this work, and it's very nice. I hope that they will have
very happy.
Yeah. I would like to invite our speaker, Professor Luca Ferranini from Politecnicum di Milano. Luca will speak about predictive control-oriented models of a domestic air-to-water heat pump under variable conditions. Luca.
Yes,
thank you.
Thank you very much, Moshe. Thank you for inviting me to this workshop. Can you see the slides correctly?
Yes, it's okay, and we can hear you quite good. Yeah.
Very good, very good. So thank you very much. This is the title of the presentation. Actually, at the end, I will also talk a little bit of tertiary use, not only domestic heat pumps. So basically what I'm talking about is control problems, in particular control of the temperature in buildings where we are using heat pumps to generate heat and radiant panels or radiators or even fan coils to distribute heat inside the building. So the general idea, so we don't need to tell so much, is reduce energy consumption while preserving comfort. And the more specific goal of this activity is to try to understand to which extent we are able to do this goal, to reach this goal through control techniques. So we are not studying any other technologies. We are just trying to push control techniques. And in particular, we do not use generic control algorithms, but real-time optimal control over a finite horizon that we call the model predictive control. So the general challenge is basically how to perform an optimal control. So how to solve an optimization problem, of course, in real time, when the model under investigation, under control is not perfectly known. So if everything is known mathematically, then we can do marvelous things. But in general, this is not the case. So basically, the challenge which is behind this work and the similar kind of works is how well we need to understand the system under control in order to control it in a sufficiently good way. This is not my concept. This is a very well concept. And the last time I heard about this was during the IFAC conference, during the plenary talk by Benjamin which is a professor from California, from Berkeley, California. Okay, so the practical problem, the practical target is to provide an estimation and prediction of the behavior of the heat pump, which is a device which is very well known, very well studied, but still not very, let me say, their model are not very used in practice. And we studied this in order to be able to decouple the generation from the delivery of buildings, of energy to the building. So this is basically, so when you need a little bit of energy in your building, you may not use the heat pump because it's not convenient. So you needed to put an energy storage device, as we have seen before, just to decouple the generation from the usage, from the delivery. There are moments where the heat pump is more efficient. It's better to use it there than store the energy and use it later. That's the main simple idea. And model predictive control does exactly this job. Makes a prediction for the future based on the model, and then trying to optimize the behavior of the system. So this is the testing facility that we use. It is actually a laboratory located in Denmark, in DTU, where there is a heat pump with a tank, and it is associated with the distribution system, which is able to serve a load which is made by two houses, one with one floor, another one with 3 floors. There is, of course, a mixing valve, 3-way mixing valve, in order to regulate the mass flows inside the house, inside the load. Again, in order to decouple even more the generation from the usage. So the tank is able to decouple, is the energy storage element, but also the 3-way valve is able to enforce a recirculation of water. So again, to reduce the temperature inside the pipelines. So the most difficult task, sorry, I come back. So the idea is how to regulate, how to control the heat pump, how to say to the heat pump, you have to work now or later to produce water at a given temperature in order to serve the load when there is somebody in the house, when somebody is providing their own desires about the profile of temperature. So we studied a little bit the main components. In this case, in this presentation, I do not talk about the model of the house, which is assumed to be fairly simple, which is usually the case for mid-term control, mid-term horizon control. So we studied the tank, the water tank, and the heat pump. So basically, we used a vertical stratified model for the heat, for the hot water tank. And we compare it with 24th order system in order to understand which is basically the root mean square error. And we see, of course, that based on the number of layers, the number of nodes that you put inside this model, you have a different quality of results. And for the heat pump, that's one practical problem, because when you buy the heat pump, you know that there is a local controller inside which is able to switch on and off the local pump, which circulates the water inside the condenser side. And there are other switches and other controllers inside that are not very well documented. So what we did is to develop a reference model thanks to some library, thermolib library, in order to model correctly the gases inside and all the phenomena. In the end, we collected the data from the tank, from the various level of the tank. We measured the electrical power, and then we managed to experimentally validate the reference model in all the ranges that we are interested in. For the heat pump control, we need a model. Usually, where sampling times are in the order of minutes, in this case, we are using 15 minutes, the COP can be assumed as a nonlinear algebraic function. And there are usually a lot of combination of possibilities to approximate the behavior of the COP. In the past, we studied linear and quadratic functions with 1 to 3 different inputs. Typical inputs are the open air, so the external temperature of the water that you have to heat, and the power itself, or the compression factor. So the main problem, so one of the problem actually in the modeling of this system, so trying to reach the goal that we set at the beginning. So what is the simplest model to achieve an optimal control is not to model the mass flows between the condenser side of the heat pump into the tank, because that's, let me say, the most straightforward way, because we have no measurement of the mass flows. So how much water is coming into the tank and is recirculating in the tank. So what we did is to model the heat as a function of, simply as a function through the COP of the electrical power, and then we distribute it in the tank as an exogenous input. So as an input of the model. And what we did is to try to understand how we have to distribute this heat between the layers and how many layers we should use with such a simple model of the system. As you can see here, there are errors in this simplification. And let me say, a good approximation is with a model of 4 layers with heat as an input and not mass flows as input, okay? And that's the typical errors that we obtain. So approximately a couple of degrees on the temperature inside the tank, which is an acceptable error. The temperatures are in the range of 40 degrees, more or less. So we set up a control problem, an optimal control problem. So we have our reference model, our detailed model of the system, and then we set up our controller. The controller is based on an estimator, a Kalman filter-based estimator, and then we have a control-oriented model, which is a simplified model of the whole system. So the reference model has actually the mass flows and the temperatures and the stratification of temperature and the heat inside the tank, all of that, while the control-oriented model has a simple tank model and a simple COP model. So that's the challenge. If our model inside the controller is fair enough to control the system and simple enough to be implemented in real time. So here there is the discussion, the description of the cost function, which is basically a combination of cost, which means electricity cost, and comfort, which is a tracking error with respect to the set point. There are some constraints on the temperatures of the zones inside the building, on the water to be used inside the radiators, and so on. So we set up in the end a nonlinear model predictive control because the system is nonlinear due to the COP and the thermo-hydraulic dynamic of the system. And then we used some, let me say, classic technique to discretize the system through a Runge-Kutta algorithm, classic Runge-Kutta algorithm with integrating shooting integral of 4. And then we solved a discrete optimization problem with a prediction horizon up to 12 hours, from 6 to 12 hours. Nothing changes. We compared what we did with this optimal control problem with the classic heating curve control, which basically it's a table, it's a function, which tells you which is the right temperature for the tank based on the external temperature, more or less. Okay, so if outside it's very cold, then you need to increase the temperature in the tank. That's it. We took this exactly from the same manufacturer of the heat pump, because this is actually what is implemented in the local controller of the heat pump. We simulated one typical day in winter where the external temperature is around 0 degrees. And then we have seen that the comfort bounds are basically easily, let me say, matched by any kind of controller. So from the optimal control down to the heating curve element, we are able to track the temperature basically inside the building. But the electrical power that we use is a bit different. Okay, so we see in the dashed line the price that we invented, the real-time pricing that we are inventing. And we see that our technique, of course, is trying to use less energy when it costs a little bit more, and vice versa. When it's a little bit cheaper, then you can use it a little bit more electrical energy. So in the end, what you obtain is that your heat pump is able to work at a lower temperature. And since the efficiency of the heat pump depends on the temperature of the water that you have to heat, you can gain a lot in terms of efficiency. Of course, so when the heat pump coefficient of performance is high, maybe you are not using that much the heat pump. So the overall saving is less if you look at the money that you spend or electrical energy that you spend with respect to the COP increase. So basically what we proved is that it's totally feasible to set up an optimization problem in real time, even with non-linear models. Our algorithms run in MATLAB on a standard PC, and they usually take less than 1 minute to run. So we are talking about a non-linear optimization problem with 20 points in the future with inside the horizon. And in the end, we are able to save a significant amount of electrical energy with respect to more traditional controllers. What we are doing at the moment, so we were encouraged by the results. So we tried to move from residential, as I said, to tertiary field. In this case, we took a building of Politecnico, which is a building with 4 stories, 18 spaces, 14 classrooms inside. And the HVAC is a classic industrial one. So you have air handling units, two of them serving 2 floors each. We have 2 heat pumps, one air to water and one water to water. There is a well in the garden to do so. And then there is a complicated system of distribution of the water through radiators and fan coil. And also the air handling unit contains also some temperature control for the water. So basically what we did is to simplify the model. As usual, what we are doing actually is to simplify the model to the most essential parts for the thermo-hydraulic system. For the building, we try to identify the main responses through the classic gray box model. So the heat transfer coefficient were assumed to be unknown, and you identify them from the data. We put a lot of sensor inside the Smart City project that Athanasius mentioned before. And so we were able to capture the main dynamics of the room temperature and the wall temperatures. In the end, we are setting up a nonlinear MPC. So the only difference is mainly the scale. Now the scale is much, much bigger than what we have seen before. And there are a little bit more devices and more industrial ones. So air handling unit, different COP, and so on. We are also trying to use neural networks, not only differential equations to model our system. And we are getting some, let me say, good results. Let me say, I think they are less good results because the quality of the tracking is a little bit worse, but the advantage is that you just take the data and magically you are able to set up a controller. So we use the neural network. We train a neural network based on the data, and then we transform the neural network model into a nonlinear model that we use into the nonlinear MPC. This is a quite innovative way to deal with this, but it's a combination of a neural network and the MPC approach. We are going to deal in the future with a more reinforcement learning, machine learning approach, even if personally I'm not so positive towards this approach, because so we just took some bites of this problem, but we immediately understood that it's less easy. For sure, it's less easy. For example, the training of control agents is more complicated. You need a huge amount of data. Even in the first talk, Athanasios mentioned this. So 1 year data is not enough. Usually for a heat pump, you need maybe a few minutes of data, and for a room, maybe you need a few days of data. But the machine learning needs a huge amount of months of data, and this is exactly what we are experiencing even in simulation. And if you make a mistake, if you are not if you happen not to use sufficiently rich data, you have an unstable behavior. So for some days, this is just a set point moving from 17 degrees to 22 degrees. You see the first days, your system is tracking very well at the set point. And after a while, something happens, something goes wrong, and you are not able to track it very well. This does not happen if you're using even a standard PID control. This means that we still have to work a lot on this subject. And also another point that is, again, disappointing me, if you zoom a little bit when you think that the system is working correctly, you see that you are not even able to track very well the temperature. So nothing important, let me say, we are talking about 0.1, 0.2 degrees. But if you zoom a PID control performance, you see the temperature perfectly tracked. So it means that we are going to study this. My expectations are not so high, let me say, but maybe a combination of model-driven, so it means equation-based controller with more data-driven, which basically means you try to fill your ignorance on the model thanks to lots of data. Maybe a suitable combination of these two approaches may have a better performance in some cases. We are looking for, let me say, these positive cases. At the moment, we are still working on that. Okay, that's all from my side.
Thank you, Luca. It's very, very, very interesting, especially that, I mean, you also have some mechanical engineering people, I mean, people that are more familiar with the thermodynamics of the system and the control, your colleagues.
I see some question on the chat. So there is one on air water heat pumps. Yes, for sure they have some limits. The one that we know that were told us by the manufacturer, we implemented them. And for the Denmark case, there is also an additional device heating the external part of the system just to inhibit the formation of icing on the external fans. We didn't model them explicitly because basically this is for us an additional electrical consumption, which is able to protect the heat pump. And that's it. And for our case, the last that we have seen, again, we didn't model it because one is water to water, and that's fairly simple because the temperature of the water is more or less constant for us. And the other one is really protected in a special building, so we never reach better temperatures, let me say.
Do you think, Luca, can you hear me?
Yes, very well.
Did you try to do it also during the summertime, meaning for hotter days? Then you will use it on the reverse cycle for cooling the building.
Yes, I understand that. No, we just made some experiments, but some simulations, sorry. But we didn't investigate that much. Let me say the COP formulas should be different, of course, but the rest of the simulation model should be the same because the thermodynamic properties of the walls and pipelines are the same. So we made just a few simulations, and that's it. So we didn't experienced any big problems. Let me say, we didn't model.
It would be interesting. I mean, we could use it in one of our buildings. That would be very interesting to do it. Yes. Maybe we should, yeah.
Could be nice. It could be nice. You have more problem of cooling than heating.
Yes. Probably. You have to understand that yesterday we had 40 degrees outside, so it would be.
we have still the heating on in Milan. So actually not in Milan, but in the north of Italy. So our heating system is still working these days. So dramatically cold.
Okay, I think that we are over. There's another question from Ellie. Do air water heat pump have a limit of the output? Yeah, we were talking about COP in water. The water seems to be higher.
Yes, this is exactly what we had. So we had the data sheet of the two heat pumps, and this one is tremendously more performant than the other one in the conditions where we simulated, which is basically in a winter day. So where air to water usually is not working very well, while water to water is a little bit more performing. Actually, this opens the way to another problem because I don't know why they installed two heat pumps, so I can imagine, but so it opens the way to how to modulate somehow, if it is convenient, the power needed between the two heat pumps. But we did not investigate it yet, this problem. So we just use them as a unique machine which is able to deliver heat, even if we model them separately.
Okay, I want to thank, as I said, it was very interesting, Professor Luca Ferragnini and all the rest of the speakers. It was very interesting. And as you can see, the energy field is very, very, I would say, there are a lot of aspects we should think about: energy storage, about energy consumption, controlling. There's a lot to do, and I hope that we will work on it. And maybe we will try to do something about cooling devices in Israel. So I want to thank all the speakers and all the people that were listeners in this symposium. Thank you very much, and see you next time on the conference, on the 8th Afeka conference on smart energy, maybe here at Afeka. Thank you very much, and
thank
bye.
You. Thank you very much.
Bye-bye.